For the remainder of this unit, we're going to be considering boundary conditions. And so up to this point, what we've been considering is homogeneous medium. So we've been just talking about a dielectric or a metal, but now we want to ask ourselves, what happens if we consider two different material regions that are adjacent to one another? And so we're going to consider two general cases. So our first case is going to be, what if we have two dielectrics that are sort of adjacent or right next to one another? So if we have then a dielectric-dielectric boundary. And so of course with this dielectric-dielectric case, we're sort of implicitly saying we have different relative permittivities. So different epsilon r values. Because if we have the same epsilon r, of course we could say we just have a homogeneous medium still. And the second case we're going to consider is a conductor dielectric boundary. And so of course this is relevant for cases pretty much, anything where we have an electric connection from the dielectric to an external circuit. So even like the simple parallel plate capacitor we saw, we're going to have an we're going to have a conductor dielectric boundary on either of the plate surfaces. So in both cases, we're going to sort of utilize certain equations. So we're going to go ahead and write those here. And then in the later videos, we're going to come back and we're going to look at these specific cases and some examples a little more closely. So in both cases, so basically the first thing that we're going to consider is we're going to utilize the fact that we can sort of decompose any field. So we're going to utilize the fact that any field, so this is electric field, electric flux density, any field at all can be decomposed into normal and tangential components. And so these normal and tangential components are then going to be normal to each other, or perpendicular to each other. So we maybe make that a little less confusing. So we're not using normal and normal. So that are, I'm missing an O there, that are perpendicular to one another. And so again, the key idea there is that we're decomposing it into these two parts, a normal part and a tangential part. Well, normal and tangential to what? As we're going to see later, it's going to be normal and tangential to our interface between our two materials. So again, we're talking about sort of an interface between these two materials. So, between our dielectric and our dielectric, or between our conductor and our dielectric. And so this normal and tangential component are both perpendicular to one another. All right, and so we could sort of write that out, and we've seen this before in a previous example way back, I believe in one of the first or second unit problems. So we can say our electric field, for instance, is equal to the tangential component of the electric field, E sub t, plus the normal component of the electric field, E sub n. And again, we'll see some more details about that as we look at specific cases. So we're also going to utilize some equations that we have found previously. So the first one we're going to use is that our electric field is conservative. And so in equation form, that means if we have the line integral around a closed path, so it's very important that we are considering this as a closed path here, of our electric field dot dl is equal to 0. And so you can find that on page 147 in the textbook. I don't know offhand where that is in the notes, but we definitely talked about that in the previous unit. The second thing we're going to use is our integral form of Gauss's law. And so what that said is the closed surface integral of d dot ds is equal to the charge enclosed. So again, that's our integral form of Gauss's law, and you can find that on page 132 in the textbook. So again, essentially what we're going to use is we're going to use these three items, this idea of decomposing the field, our conservative nature of the electric field, as well as our integral form of Gauss's law, to sort of simplify how we can approach these two general cases of our boundary conditions.